A comet just flared to life near the sun, its tail now wider than 5 full moons. Days later, the sun fired back with a powerful solar storm, aimed straight at the comet's path. What happens when a wave of starfire collides with a frozen visitor from deep space? If you're into real-time cosmic drama, comets, solar storms, and the science behind it all, make sure to like, follow, or subscribe. This is Space Happening Now, and we're watching it unfold together. On October 21st, 2025, Comet Swan will swing closer to Earth than ever before, just as solar plasma races to meet it. What happens when a wave of starfire collides with a frozen visitor from deep space? This isn't science fiction, it's unfolding now, live in the sky, and visible to anyone with a telescope, a camera, or simply a clear view of the stars. At first, Comet C/2025 R2 Swan looked ordinary, a faint smudge moving steadily through space, barely visible with a telescope. It passed perihelion, its closest approach to the Sun, at a distance of just 0.5 astronomical units, closer than Mars ever gets to Earth. Its brightness hovered around magnitude 7.4, well below naked eye visibility. But comets are built for surprise. 2 weeks after rounding the Sun, something changed. On September 26th, amateur astronomers in Japan and Australia spotted a sudden jump in brightness, nearly a full magnitude. By nightfall, global astronomy forums were buzzing. Swan had surged to magnitude 5.7, just within naked eye reach under dark skies. This wasn't a glitch. Outbursts like this suggest deep changes inside the comet's nucleus. Frozen gases, locked away for centuries, cracked open under solar heat, blasting dust and vapor into space. The coma, the glowing cloud around the core, expanded, and the tail began to grow. Every observation became a clue. Thermal fractures, active vents, maybe even structural collapse. Swan had entered a new phase. It was no longer just passing through the solar system. It was putting on a show. By the end of September, Swan's tail had transformed. What started as a faint trail now stretched more than 2.5 degrees across the sky, long enough to lay 5 full moons end to end. For the first time, casual observers could trace it with binoculars. In dark skies, even a simple camera on a tripod could catch its streak. The scale changed everything. This was no longer a point of light. It was a full structure. Dust, ice, and ionized gas trailing behind the comet like a celestial banner. The dust tail, heavier and sunlit, formed a wide golden fan. But the ion tail, composed of charged particles, danced to the rhythm of the solar wind. It could ripple, bend, or snap away entirely under the right conditions. Observers began to notice dynamic features: knots of dust, shifting streamers, and sudden bends. Night after night, Swan changed shape. Amateurs across the globe started stacking images, comparing notes, and creating time-lapse videos that revealed motion hour by hour. Colors hinted at the chemistry inside: soft blues from ionized carbon, warm tones from reflective dust. The comet wasn't just glowing, it was telling a story shaped by sunlight and space weather. And all of it, from core to tail tip, was drifting toward Earth. 2 days after Comet Swan lit up the sky, the Sun answered. On the morning of September 28th, without warning, it unleashed a powerful M6.4 class flare, a burst of radiation that lit up space weather monitors in seconds. From deep within a twisted sunspot region, a bright flash erupted across the solar surface. But the real drama came next. A coronal mass ejection, a colossal wave of charged plasma, burst from the Sun's atmosphere, expanding fast and wide. It wasn't aimed at Earth. It was heading somewhere else. It was heading towards Swan. At the NOAA Space Weather Prediction Center, alerts flashed. Solar physicists watched as images from NASA's coronagraphs confirmed the trajectory. A fast-moving blast of solar wind was now on a collision course with the same quadrant of space Swan was gliding through. 2 cosmic forces, one ancient and icy, the other fiery and magnetic, were about to intersect. No one could say exactly what would happen next, but one thing was certain. This wasn't just a comet anymore. It had become the focal point of a live solar system experiment, one playing out in plain sight across Earth's skies. By September 29th, the countdown had begun. The coronal mass ejection, launched from the Sun just a day earlier, was now racing toward the same stretch of space where Comet Swan drifted, tail exposed, glowing, and vulnerable. It wasn't a direct hit. Not exactly. Solar eruptions don't travel in straight lines. They twist, expand, and spiral through the solar wind, dragged by tangled magnetic fields. But models showed the CME's front would likely sweep through Swan's vast ion tail, a ribbon of charged particles stretching millions of kilometers behind the comet. And that's where the real drama lives. Unlike dust tails, an ion tail isn't just matter, it's electricity. It forms when solar ultraviolet light rips electrons from gas molecules streaming off the comet's core. These ions cling to solar magnetic field lines like a kite on a string, but when a CME arrives, it can snap those strings in an instant. If the magnetic orientation of the CME is just right, pointing southward, it triggers a phenomenon called magnetic reconnection. It's like a cosmic circuit breaker blowing. The field lines from the comet and the CME collide, reconnect, and violently reconfigure. The result? A section of the tail can snap off entirely. This process can happen fast, within 90 minutes, and it's visible. Observers could see sudden kinks, sharp bends, or even a glowing cloud drifting away, detached from the main tail. For astronomers, it's a rare gift. For sky watchers, it's a spectacle in motion. Now, all eyes turn to the sky, not just to see the comet, but to witness what happens when it gets caught in a solar storm, a live experiment unfolding at 900 kilometers per second. On October 21, 2025, Comet Swan will make its closest approach to Earth, just 0.25 astronomical units away. That's about 39 million kilometers, or roughly 100 times the distance to the Moon. For a comet, that's close, very close. But proximity isn't the only reason this moment matters. The geometry lines up almost perfectly. Swan crosses the ecliptic, the sun's equatorial plane, just as solar activity peaks. It flies straight through a zone charged with magnetic chaos, the same corridor where solar wind, plasma, and the heliospheric current sheet collide. And it's not alone. On the same night, the interstellar object 3I/Atlas reaches superior conjunction, aligning on the far side of the Sun. Though separated by millions of kilometers, these two travelers, one native, one alien, appear to move along the same celestial highway. To astronomers, this is more than coincidence. It's a statistical anomaly. The odds of a bright comet and an interstellar visitor aligning in the same month under a new moon are vanishingly small. But the timing couldn't be better. With the moon completely dark, skies will be at their clearest. Southern Hemisphere observers, from Buenos Aires to Perth, will have the best views, with the comet rising early and stretching high by dawn. In the Northern Hemisphere, visibility improves as Swan climbs higher each night. And thanks to the close distance, even basic equipment, binoculars, small telescopes, DSLR cameras, will be enough to catch it. This isn't just a passing comet, it's a live performance, playing out under the darkest sky of the year. This isn't just a show for professionals with million-dollar telescopes. In fact, some of the most valuable data may come from people watching from backyards, rooftops, and rural fields. Across continents, amateur astronomers are already syncing observations, logging the comet's position, capturing its tail, and comparing night-to-night changes. Time-lapse images, color shifts, and sudden kinks in the ion tail could offer real-time clues no satellite can catch alone. Even a tripod-mounted camera or binoculars can contribute. Every image, sketch, or timing report becomes a pixel in a much larger picture. The universe doesn't schedule these events for us, but this time, the timing is perfect, and the tools are in your hands. Despite the excitement, many questions remain. We still don't know if the solar flare caused Swan's earlier outburst, or if it was just cosmic coincidence. We can't say for certain whether the CME will slice through the ion tail or miss it by a fraction. Even the structure of the tail itself, its twists, disconnections, and chemistry remains partially hidden, revealed only frame by frame through global observation. This isn't a scripted event. It's a live experiment in solar system physics. The models offer guesses, the skies hold the answers, and those answers are coming soon. Comet Swan is more than a rare visitor. It's a messenger from deep space, caught in a moment of high drama, bright, active, and now tangled with the solar wind. What happens next isn't up to equations or forecasts. It's unfolding in real time, and for once, we get to watch. Whether you're standing under city lights or out in the quiet dark, you're part of the story. Aim your lens, tilt your binoculars, mark the tail's curve tonight and again tomorrow. Because in this fleeting alignment of comet and starfire, the universe is putting on a show and you're invited to record it. If you want more stories like this, grounded in real science, driven by wonder, like, subscribe, or follow. The sky is always changing, and we'll be here to track it with you.